computation course. So x1 into x2 is different from x2 into x1 because the word x1, x2 is not the same as the word x2, x1. So that's the non-commutative polynomial ring, and will this work? Okay, it will work. So this is also called the free non-commutative ring because it's over the free monoid. X1 to xn generate all possible words without any other relations. And the two well-known examples, especially in the commutative setting, are the permanent polynomial, which is closely related to counting matchings in bipartite graphs. If you do 0-1 substitutions, it's exactly that. And the determinant polynomial, which is like ubiquitous in mathematics. So you could talk of these two objects also in the non-commutative setting. And Nizam's question is, can you show that the permanent polynomial or even the determinant polynomial in the non-commutative setting does not have small arithmetic circuits? Where by arithmetic circuits, what you mean is you start with scalars and variables, and you can add and multiply, and in the end, what should come out is the permanent polynomial. In the intuitive sense, arithmetic circuits. Is there any water bottle? Okay, so here is a quick run through the definitions. Non-commutative arithmetic circuits look like this. They look exactly like commutative arithmetic circuits do. Here, things are flowing from top down. Usually they flow from bottom up, but I copied this slide from probably Abranil's slides or something. And he prefers this. So x1, x2, x3 are the inputs. The plus gate adds x1 and x2. The multiply gate multiplies x through x3 and then x1. It's ordered. The inputs are ordered right to left because you're coming that way. And the circuit output is what I've written there, x1 plus x2 plus x3, x1. That's what comes at the output gate, which is the bottommost gate, times x1 plus x2 plus x3, because the output gate is a times gate. Another important, interesting model of computation is what Sumedha in the morning spoke about, but in the Boolean setting. Algebraic branching programs are essentially like what she described, except that they're really like automata here. The only difference is that instead of accepting words, you have plus here. So it's going to sum up all the words that it accepts with possibly scalar coefficient setting in front. So let me explain quickly. So S is the start state, and we're assuming T is the only accept or final state node. And you go over all S to T paths, multiplying the linear forms that you see along the path, and you add them all up. So you have x2, x1 to x1 cube is the topmost path, and the bottommost one is x1, x2, x1 plus x5 into x2. Sorry? Regular. It's like finite automata, except that they don't, I mean, you're also doing some arithmetic. Thank you. Okay. And the size of the algebraic branching program.
Question there.
Sorry. Oh, sorry, I missed you.
That there is a construction. There is a construction for AVPs for calculating the determinant, but does that not work in the non-commutative setting?
Sorry, say that again.
So there is a small AVP for computing the determinant, but does that not work in the non-commutative setting?
You can prove exponential lower bounds.
Oh, I see.
That's true. I'm just describing the models of computation. And I think I'll come to that point. Because of non-commutativity, we are thinking thinking of left to right. And there's another important point here that you can also think of automata in terms of matrices, because you can think of the rows and columns as labeled by the states of the automata, and the matrix mxi, basically the entries of that matrix are scalars with it attached to the variable when you do it one state to another move. So the ijth entry means that if you go from state I to state j, whatever is the scalar entry will get multiplied with xi. It's easy to imagine. So running an automaton on a word is like multiplying matrices, usually Boolean matrices, but here arithmetic entry matrices. I hope it makes sense. Okay, I also wanted to mention some important results that are known. The commutative determinant has a very nice algorithm due to Meena and Vinay. On the other hand, in the non-commutative setting, Nizan showed that algebraic branching programs require exponential size. It's basically like the automata lower bound for context-free languages for the palindrome polynomial, for the palindrome language. Essentially the same kind of idea lifts to a rank argument, and you get the lower bound proof there. So ABPs are much weaker than non-commutative ABPs are much weaker. Small arithmetic circuits, you can easily construct one. What else? And ABPs are nearly as powerful as small degree circuits in the commutative setting. So it's like a crash introduction to the model and a few basic results. I should mention the celebrated LST result, which is after a long gap, they proved this very important. Limai, Srinivasan, and Tavenas, Srikanth and Nutan are here for constant depth arithmetic circuits, super polynomial lower modes, which I think Ramya also mentioned in the morning. Yeah, okay, so now we are all set to do some math. So I'm going to talk about skew polynomial rings. So non-commutative computation was interesting for several years for me because it was really very combinatorial, and you could apply automata theoretic ideas and prove interesting things. But then in the last few years, we realized that you need a little more math than that. And skew polynomial rings are a fascinating class of objects introduced by Oystein-Orr in the 1920s and apparently also Wedderburn around the same time. And the broad goal, their goal was to construct non-commutative division algebras, division rings. So what is that? I should, so just like you have fields, the question is, if you have non-commutative rings, can you construct non-commutative division rings where you can both add, subtract, multiply, and divide by non-zero elements? And what are nice examples of such division rings? You can express in the case of a field, for example, if F is like maybe rationals or something, then we know that A by B, they have a nice normal form where A and B are integers. You can even reduce it to the least common form, and it's kind of unique. So the same question is not clear whether you can do that at all in the case of division rings, and what are the conditions that you require of the ring to construct such objects. And that probably was the main motivation for Orr to invent these rings. So let's understand the definition. So K is any commutative field. So K is either a finite field, integers modulo P for a prime P, or the rationals. Sigma is an automorphism of K. So what is that? It basically means sigma is a mapping from K to K. It's a 1 to 1, it's on to, and it preserves the field operations. So it's a bijective homomorphism. You can add here and apply the map, or you can apply the map and add there, and for multiply also. So 1 will go to 1, where 1 is the identity, multiplicative identity. 0 will go to 0, which must happen in the case of rings also. But so sigma is an automorphism of K, and the skew polynomial ring Kx sigma is like the polynomial ring Kx. Kx is the univariate polynomial ring. All polynomials of the kind x square minus 1 or x square plus 1 and stuff like that. But here you tag along this automorphism sigma as well. And you think of the elements of the skew polynomial ring as all left polynomials, which are basically, you write it in a kind of normal form. You put the coefficient and then the variable power. So any element looks like f0 plus f1x and so on, where the fi is the scalars. Addition is just the usual addition. So you will just add component wise, but multiplication has a twist to it. It's a skewed multiplication by sigma. So x into a is sigma a into x. So sigma could move a, sigma need not fix a, and therefore it's not a commutative ring anymore. And if sigma was identity, it's just the standard polynomial ring Kx. So here is a nice example. You could take F to be the field of complex numbers, and sigma is the automorphism that maps every complex number to its complex conjugate. So a plus ib goes to a minus ib. Then you can check that, well, you will get by definition a skew polynomial ring. So if there in that polynomial ring, x into I, where I is square root of minus 1, will be minus I into x. Immediately funny things start happening. So you take the polynomial x square minus 1, it factorizes not just as x plus 1 into x minus 1, but uncountably many ways. So for every omega, every point on the unit circle, every omega of absolute value 1, it's x minus polynomial at a field element. You can't directly substitute it because it doesn't really respect sigma anymore. So the right way of evaluating a polynomial at a scalar is you left divide that polynomial. By left divide, what I mean is, so if you have a polynomial fx in Kx sigma and you have x minus alpha, you can left divide f to get a unique remainder. Right divide. We are right dividing f by x minus alpha, getting a unique quotient and a unique remainder. You can prove that holds. Because sigma is an automorphism, you can do all these things happily. You can also right divide it, but then the quotient and remainder could be different. Okay, so we will, by convention, think of the roots of f as those alphas, such that when you right divide f by x minus alpha, the remainder will be a scalar. Because r has to have degree less than the divisor, it will be a scalar, r should be 0. And in that sense, x squared minus 1 has all these complex numbers as its roots. So it looks very bizarre. But it turns out that it's not all that bizarre, because everything that is above in the positive side is in some nice sense conjugate to 1. And everything that is below with negative complex component is conjugate. Conjugate not in this complex, well, in some sense, yeah, which I'm not going to define. So it still, in some sense, has only 2 roots up to conjugates. All these infinitely many roots get clubbed into one equivalence class, and still factorization and even unique factorization makes sense. for such polynomials. But the important thing is that left division and right division are different, but it behaves like a Euclidean domain. You can right divide, get a unique quotient and unique remainder, and therefore you can talk of the right GCD of two polynomials and the left LCM of two polynomials, and many things that we encounter when we look at usual polynomial rings crop up there with this left and right business, putting it very vaguely. Okay, so here are some more examples. So you can take the finite field fq to the m. So you can think of q as a prime and fq to the m is obtained by taking fqx quotient and by a degree m irreducible polynomial over fq. And the map A maps to A to the Q is the Frobenius automorphism. And you know that, well, I'm just pointing out also that it has a fixed field, that there are points that are not moved by the automorphism. And the fixed field is precisely F sub Q. We know that because of Fermat's little theorem. X to the Q minus X has only those things as roots. And you get another skew polynomial ring. And I wanted to point out one more nice thing here. So like in the previous example, sigma square was identity. Here sigma to the m is identity. And there's something more here, that if you look at all automorphisms of K with FQ as the fixed field, all automorphisms of FQ to the m with FQ as the generated by Frobenius automorphism. So it's a cycling group. The Gull group is cyclic. Sorry for throwing some big sounding words. Basically, there are no other automorphisms other than the power of sigma. And the other nice thing is that the set of all elements of this ring R, which commute with every element of the ring R, is this polynomial ring F. I should have written Q. Q is missing there. F sub Q x to the m. X to the m because when you move over, because x to the m a will become sigma to the m applied to a x, and sigma to the m is identity, so it will be ax. So x to the m, ax to the m, sorry. So every a essentially commutes with x to the m. So this is a set of all polynomials which commute with everybody in the ring R, and that's important for us. Here is another construction. This is the one that I'll use later as well. You take the rational numbers, attach a commuting indeterminate z to it, and also the mth root of unity omega, that is k. So k is this finite extension of q sub z. F is a fixed field. The automorphism sigma simply maps omega to the j, where j is something that's relatively prime to m. So again, this is a cyclic extension, K over F. The set of all automorphisms with F as fixed field are basically powers of sigma, and sigma to the m is identity. Feel free to stop me and ask any question. I'll just slow down. Maybe I'm going a little too fast. Everything makes sense? Okay. Okay, so I want to talk of some division rings because I'm building towards this Amitsur-Levitsky theorem, which I need for PIT. Okay, so this is how you build a field extension in the commutative sense. You go modulo the ideal generated by an irreducible polynomial. That gives you a field. What do we do here? As I told you all this stuff. You can right divide f by g and you get a unique quotient and remainder. You can also left divide, but because you can do these things, the left and right ideals are principal ideals generated by a single element. So left ideals look like R into F, right ideals look like F into R. And if this polynomial F happens to be a central polynomial, namely, like I said, something in Fx to the m in this example, then I can go modulo the ideal generated by a central polynomial. And I will get a ring. And my question is, when does it give a ring? And there is a nice characterization by Wedderburn, whose details we can't go into. It's not a hard theorem. What it says basically is that if R is the skew polynomial ring where sigma is an automorphism whose order is m, and f is a fixed field of sigma, and k over f is a cyclic extension. That means the only automorphisms with f as fixed field are powers of sigma. Then if you take x to the m minus a, that will, for any a and f, that will be a central polynomial. So we can go modulo the ideal generated by x to the m minus a. It will turn out to be a division algebra if all the powers of a are not the norm of any element of k. So it's a very technical looking condition. So we need a condition like this because there are two fields involved. It's not just a any element, let's call it b, looks like b into sigma b, etc., sigma to the m minus 1b. The product of all automorphisms images fixed field. So the norms that you can get by computing this product, the set of all norms that you get should be a proper subset of f, in fact a proper subgroup of f, and any element of f which is not such an element you can use to get a division algebra. Any questions? Okay, let's go ahead. So we will force it, but yeah, it depends on in general, it depends on the field and on both k and f. So let's look at some constructions. So this is the example that I took earlier, and this is something that you all might have seen. So let's say j is the new variable. So I've deliberately used j instead of x here. So j into I is minus I into j. And that's what defines multiplication in the ring R. And we're going to take A to be the element minus 1. So minus 1 will play the role of that element here. And that's because the norms of all elements are the absolute, I mean, A plus B into A minus B is the norm, and that's A square plus B square, which will be non-negative. So it will never be minus 1. So J square plus 1 is a central polynomial, and the norm of any element is just what I told, because A plus BI into its, you apply sigma to it, you get A minus BI, and there are nothing else, no other automorphisms. So this quotient is a division algebra, and it's a very familiar division algebra. It's basically the division algebra of all real quaternions. Capital H stands for Hamiltonian. No. H is simply because it's named after Hamilton. It's real quaternions. Hamiltonian is something else. So K is I into J. And the algebra is basically C plus Cj, but when you replace C by R plus Ri, you have these 4 things in it. And here is the other construction which I'm going to use in a bit. K is the field I mentioned earlier, Q adjoint with the mth root of unity and a commuting determinant Z. And the fixed field for sigma, which maps omega to the J, will be Q adjoint with Z. And it turns out, which is not difficult to check, that again, this z will play the role of a in that Wedderburn theorem. So x to the m minus z is a central polynomial, and by Wedderburn's theorem, this quotient will be a division algebra. You can see that it's m square dimensional algebra over f. Why? Because there are 2 degrees of freedom. You have powers of omega. There are m powers of omega 0 to m minus 1, and m powers of x as well. So omega to the j, x to the l, there are m square choices, and all these things together give you an m square dimensional algebra. And what's more, it sits nicely inside the S by S matrix algebra. So we have 2 fields, one is K and one is F. F is Q adjoint with Z. K is Q adjoint with omega and Z. Consider S by S matrices over K. So whatever, let's call it MSK. So in what sense does it sit inside that? So we're going to argue that this division algebra, which is K x sigma quotient x to the m minus z, sits inside homomorphically, so embeds inside this. And the mapping is very nice. X goes to the matrix where you have zeros along the diagonal, ones just above the diagonal, z at the bottom left corner, and zeros everywhere else. You can see that x to the m will map to z times the identity. This, yeah. And all the scalars, if you take any b in K, its image will be the diagonal matrix, which is b, sigma to the m minus 1b. I should have said m here. So these are all m by m matrices. So I get m by m matrix representation for this division algebra. It's all sitting inside the F linear combinations of the image of all these omega to the j, x to the l, all these matrices will give me a copy of the division algebra sitting inside m by m matrices over K. Okay. And the nice thing, one more nice thing about this is that if you take this as your, so let's take the basis as all the, so let me call this map M. So let's say M omega to the J times M x to the L. This is the basis, J and L varying from 0 to M. If I take the F linear combinations, that gives me a division algebra sitting inside M by M matrices. If I take the K linear combination of these matrices, it gives me the entire matrix algebra. I get the whole of the M by M matrices over K. And there's a reason for that, which I will not explain. I think I've lost too many people. I'll try and get back some of you. Let me see. So the main thing to take away, which I'm not shown here, is that it's sitting inside the bigger algebra of M by M matrices. Okay, let's go to the Amit-Sulevitsky theorem. So F is a non-commutative polynomial, let's say given by an arithmetic circuit, and let's say it's the degree of that, syntactic degree of that circuit is not too large, it's polynomially bounded in the size of the circuit. Then you get a randomized polynomial time identity test because of this theorem. What this theorem says is, one half of this theorem at least, what it says is that if you have a degree d polynomial, which is non-zero, non-commutative in this free non-commutative ring generated by x1 to xn, then it does not vanish on d by 2 plus 1 dimensional matrices. So what you could do is simply substitute for the variables x1 to xn d by 2 plus 1 dimensional matrices with, say, commuting entries, variables as entries, and the problem reduces to this standard commutative PIT, and you will get a randomized polynomial time identity test for it. Oh, sorry. When did it turn? Oh, I'm holding it the other way. So this is what I just told you. Very easy polynomial time identity test. So suppose K is the field which we just spoke about, K, Q, omega, Z. Let's see what we get from this. If K was that field, then I just need to substitute random matrices from scalar matrices from over K, and of course I'll make the choices finite like we do in the Schwartz-Zippel lemma for every variable, and I'll get a scalar substitution which over the field K says that the value of the polynomial is non-zero. I'll get the evaluation on that random matrix substitution and m by m matrix with non-zero entries in it. What I can do is I can take that matrix and write it in this basis, in this division algebra basis which we just computed. Okay? Am I making sense? So you take those scalar matrices and write it in this division algebra basis. Okay, how do I explain this? I must first run the board and then explain. So okay. So what we have got is for x1 we got a matrix A1, etc. For xn we got this matrix AN. And what we saw is f of A1 to AN, which is some matrix A, is non-zero. And this matrix A, of course, everything is m by m matrices over K. But these matrices we can write, so A1 we can write as summation, let's call it Yij, and let me name this matrix as M, okay, I don't want to use J, Yjl, Mjl. So I can find all these, I can express A1 using this, because this is also a basis for that m by m matrix algebra. So each of these AIs I can express using the MJL basis, and what I can do now is I can make the first of these, let's say the Y11 or Y00 as an indeterminate. I get a univariate polynomial, and it's a small degree polynomial. I just need to try degree plus 1 many different points to get a non-zero choice for it over F. So I'm now trying to get a linear. So these YJLs actually live over K because these matrices AI are here, and this is a basis for this algebra. But now I want to get a linear combination over F. And what I can do is point by point. I'll make one of them a free variable. I'll get a univariate polynomial and look for a substitution from F. And since the degree is small, it's univariate. Small degree, I just need to take degree plus 1 many choices in F, and I'll find one point where the output is still non-zero. So like that, I can make sure that all these Yijs are now replaced by Yij primes which belong to F. What do I get as a result? I get a division algebra substitution instead of the matrix substitution. Okay, it's not a big deal, but I find it nice. I have just summarized whatever I told you in 2 lines. So here is a polynomial version of the Amit-Surlevitsky theorem. So if you have a non-commutative, non-zero degree D polynomial and K is large enough, I did it for this particular choice of K as rationals, but you can basically do it in any setting really. Only when you choose sigma, you have to choose it carefully. If K is a field of finite characteristic, you have to be careful when you construct the division algebra, but otherwise you can do this. So the basic point is that I can do random substitutions of degree d by 2 polynomials, univariate polynomials, except that there is a sigma that is tagging along, where that sigma is of order d by 2 plus 1, an automorphism, non-trivial automorphism. And the reason I find that this theorem interesting is that if you want to deal with the high degree case, which is still an open problem, at least this gives a chance of thinking of substitutions as coming from univariate polynomials rather than the curse of matrix substitutions, which are huge objects. If D is large, there could be a compact way of representing these polynomial substitutions. I think it's possible, yeah. Or it may be possible. Okay, moving on. I don't have much time, so let me try and I'll just stop wherever I run out of time. Doesn't matter. I got across one division algebra construction, and I told you a version of the Amit-Surlevitsky theorem using polynomials. I'm happy. So let's read the Bressard-Klepp theorem. It's a nice theorem. So suppose K is an infinite field, and you do T by T matrix substitutions for the variables. So you're going to get matrices as output. The question they asked was, what can we say about the kind of matrices that you get as the range? It turns out that if you take the K linear span of the range, then it's exactly one of the following. If it could be 0, for example, if F is a 0 polynomial, or if F is an identity, polynomial identity for T by T matrices. So it could be 0, it could be all scalar matrices, all diagonal matrices with the same scalar sitting on the diagonal. Or it could be all trace 0 matrices. Or the span will fill the whole of matrix algebra. I find this very interesting and the nice analog of, a kind of generalization, a true generalization of Schwarz-Zippel. So how do they prove it? I just want to give a small idea of what they talk of what they call a Lie ideal. So the Lie bracket, or simply the commutator AM minus MA. So M is any matrix, A is any matrix from this linear subspace L. AM, the commutator AM is AM minus MA. So for every M, if AM minus MA belongs to L, you call it a Lie ideal of the matrix algebra MTX, MTK. So the nice thing is, and it's not hard to prove, you can show that the range of any non-commutative polynomial is a Lie ideal if F is a degree D polynomial, of course, for any infinite field. Actually, you don't need infinite field. You just need the field size, the characteristic to be suitably whatever within D, and you can work it out. But since they want to state it for every polynomial, they have written it like that. So, okay. And then there is another theorem which says that there are exactly 4 Lie ideals inside D by D matrices, precisely the ones that are listed above. So the algorithmic question is, can you find out which is which? Of course you can do it if you do random substitutions. It's not at all difficult. That's easy exercise. But with Avranil, Rajit, and Partha, we considered the question whether you can do it for ABPs deterministically. And we can, for characteristic 0 fields, we can do it. So here is, I'm trying to describe the algorithm here. Let me see. And oh, sorry, we can't do it for all matrix dimensions. We need T to be sufficiently large so that, otherwise it's only random substitutions work. Because we will need matrix substitutions which involve the degree of the polynomial and the size of the ABP. So we need matrix substitutions at least D. So the first two cases are very easy. Scalar matrices, in fact, non-zero is trivial because that's simply Amit-Surlevitsky. Scalar matrices, you consider the polynomial ZF minus FZ, which is non-zero, and if T is more than D by 2 plus 1 plus 1, that case can never happen. So those cases can happen only for when T is smaller than the degree, because polynomial identities can happen, funny things can happen. The interesting case is the trace zero case. And there, I think it was Rajit, if I'm not mistaken. Where is Partha? Oh, very clever trick that he found. Where, am I right? So this idea that, the two ideas that are used here. So when you set multilinearize using matrix substitutions, normally you put so maybe I need to write something very briefly, but I'm almost running out of time. I don't know where to go. Okay, so I'll just wave my hand. So the idea simply is that there are two ideas. One is that the trace of a product of matrices is invariant under cyclic shift, because trace AB is equal to trace BA. And the second idea is that a second observation is that if F has a small ABP, then you take any cyclic shift of all the monomials, degree D monomials. So if you shift by I places, that new polynomial which is obtained by cyclic shift also has a small ABP, polynomial sized ABP. And the point is that if you add up all the cyclic shifts, if you do the right matrix substitutions which correspond to set multilinearization with cyclic shift, you will bring all the interesting things to the diagonal. So the trace will reflect whether it is zero or non-zero. Vague explanation, but so basically what it means basically is that if F has a small ABP, then this new polynomial, F to the tau, where tau is over all cyclic shifts, is not identically zero if and only if trace of F under any matrix substitution, the T by T matrix substitution, is not identically. I mean, this is identically zero if and only if the trace for all matrix substitutions is zero, where the matrices are of dimension more than the degree. Sorry. Okay. We have only 5 minutes left, and so there is this other kind of skew polynomial ring. We saw only one half of the story. So skew polynomial rings actually look like kx sigma comma delta. So it's not fully skew yet, it can be skewered more. So delta is a derivation. So it follows, it's a linear map on K, and it follows the rule delta AB is sigma A delta B plus delta AB. It's a sigma derivation. So if sigma is identity, it is just called a derivation. And the ring multiplication has this additional twist to it. The derivative of A also pops out. Okay, so this is the more general form of the skew polynomial rings. And maybe this is like a motivating example or demotivating, I don't know. So if you take K to be the rational function field in the indeterminate Z, and delta is just the usual derivative, d by dz, and sigma is identity, then this is actually what is called the differential operator ring. And you can see that d by dz is actually a commutator of x and xa minus ax. That's what it will turn out to be. Commutators are closely connected with derivations. Okay, so non-commutative rank. I don't think I have time to bother you with that. So this is the so-called Edmonds problem, the non-commutative rank problem. So for any ring R, you can always define the inner rank of that matrix. It's basically the least R says that you can factorize the matrix A as a S by R into a square matrix A, let us say, S by R into R by S. The least R says that you can do that is called the inner rank. And the matrix A is called full if its inner rank is S. Square matrix is called a full matrix if its inner rank is S. Well, these are so maybe I should just shut up. Okay, I'll just show the. I'll skip all this because there's no time to really tell you anything. I just wanted to mention that what I showed you, that trick of going from K to F is from KV's paper, IQS, the Ivanios Xiao Subramaniam paper on non-commutative rank. And they use this matrix construction, this division of algebra construction crucially in their paper. So, okay, let me just cut the story short and tell you that there is this. So, if you want to do PIT in the non-commutative setting, if you have n variables x1 to xn, the substitution xi goes to x to the I y gives you a reduction to bivariate polynomial identity testing. That's because it's a homomorphic embedding. Two things can never become equal. But what we want is something from n-variate to bivariate, which will even preserve the ranks of matrices, or in particular, it will map full matrices to full matrices. And it turns out that Kohn has this really amazing result. So this shows that the usual what I wrote there does not work. It does not preserve ranks of full matrices. But this does. You can see commutators popping up there. In fact, this can even honestly embed K with infinitely many non-commuting variables into K with just two non-commuting variables, such that it preserves the ranks of matrices. The ranks in the sense that I defined, but because these rings are very nice and they have what are called universal fields of rank fractions, they're almost like the ranks that we understand over fields. Because of this, we can, yeah, it's almost done. Sorry. Sorry? What did I say?
Square bracket? Commutator, right?
Square what?
Zi goes to
The commutator. The X, yeah, the commit Lie bracket. No, not commutator. Just simply call it commutator. So I'll skip the proof. It uses skew polynomial rings of the other kind using delta. So because of this, just by reading this theorem, you can give a deterministic NC reduction from the n-variate non-commutative rank to the bivariate case. I'll stop at this point.
Questions? Okay. The nearest one.
Yeah, so just to understand, so you mentioned this skew range as being a good non-commutative setting. So can one recover some of the deterministic algorithms we have as kind of an instantiation of this, like the
I
black
don't
box or
I
something?
haven't thought about that. Like which ones do you have in mind?
I don't know. I guess for spams or yeah, even the black box ABP thing.
I have not really. You mean the hitting set construction?
Right.
I think it may be possible, but what I had in mind when I said that is handling non-commutative PIT for large degree circuits.
Right. Okay.
I have not tried it, but it may be possible. But if it's just going to mimic that construction, I don't know. It's worth it, but if it can give a new perspective, it may be interesting.
Okay.
Hi. Here. So the Amit-Levitsky theorem says that any non-zero polynomial you can do matrix substitutions, random substitutions, and that would be then f would not vanish on random matrix substitutions.
Provided the dimension is large enough,
Uh-huh.
and provided there are enough elements on base field. Otherwise, you may have to go to a field extension.
Okay.
You need more than you need to use basically Schwarzschild on the individual entries which are commuting variables.
I see. So I mean, naively, it felt like Amit-Levitsky is the analog of Schwarzschild, but you said that the Bessar-Klepp theorem is the right analog for Schwarzschild.
Okay, maybe no, analog is probably not the right word. The right generalization.
Okay.
Because
in what sense?
there's much more interesting of non-commutative polynomial than the case of a commuting polynomial. It's just scalars. It's either all zeros or it's non-zero. There's no structure that you can recover there. In that sense.
More questions? Conduct at 3:30 for Shrikant's talk.